So today we're going to talk about making an orthogonal basis from an existing basis, and we're staying in the same span of things. Now, I just said a lot of things. Let's just break that down a little bit. So we have these two vectors, and these two vectors that are given to us, first of all, they're independent, so it's an efficient span, it's a basis, and they span R3. We just have three things. So these two vectors are going in two different directions. We want to take those same two vectors and kind of make them exist on a plane, but I want to make those two vectors orthogonal, right? And by orthogonal, you know that means that they are kind of perpendicular, right? So how do we do that? They still have two pivots. There's a pivot in the first row, and there's probably going to be a pivot there if I were to do some reduction on that. So they are independent vectors. So I drew on this earlier, and let's see if I can change this up a little bit. Whoops, maybe I can't. So we have this first vector, and that first vector is vector 1. So that first vector is, I wanted that to be yellow. So that first vector is 1, 1, 0, right? So there's my first vector, my yellow vector. We want to find, when we find y hat, we're finding a projection of one vector onto another. So we have these two vectors. We have the yellow vector and we have this purple vector. Those two vectors are not orthogonal right now, right? But they do make a plane. So since they do make a plane and they span all of R2, I can still make them stay in that same plane, and I want to change them so that it still forms a basis. It's still going to span. It spans all of R2, at least, and it's a subset of R3, right? So it's going to span all of R2, right? I can get to any point in R2 because I have two pivots. So what I want to do is I want to figure out, well, how am I going to make those things orthogonal? They're not orthogonal right now. So we're going to find the projection. So y hat is found by taking x2 dotted with vector 1, and x1 is going to be the same as vector 1, right? And then we're going to expand that out until, and that's my C1 value right here. How much am I multiplying that by? I'll just use my pointer. How much do I have to expand that yellow vector out so it's going to fall right underneath this purple vector? And that's our C1 value. And the new y hat, I made that blue to see that that's how far I have to extend that out, and that's my vector. And now, if I project that one down onto it, that's going to be the y hat. The projection is going to be this new vector. And that's going to give us that. So that's going to be the y hat. And the new vector is going to be the subtraction of x2 minus y hat. Okay? So that gives me the new vector right here. So to find a vector that is going to be orthogonal to it, we have one, and we're going to still make this thing span in R2, and it's going to have a three-dimensional vector. So when you do that, so if we throw in what we have, we know that vector 1 is, what do we have? 1, 1, 0. And vector 2, x2, is 2, 2, 3. So we're going to throw that in. First of all, we want to find out what y hat is. So we're going to find the value of that constant. And so when I find the dot product of those two vectors, x2 and v1, what we get is we get 4 halves times vector 1, which is 1, 1, 0. Okay? So that gives us 2, 2, 0. And so that's going to be the y hat value, 2, 2, 0. So when I throw in, if I want to find out what the orthogonal vector is, we're going to take our given vector 2, 2, 3, and we're going to subtract 2, 2, 0, and then we would obviously get 0, 0, 3. So when we looked at these two vectors from the beginning, A, graphically they're not perpendicular, and then B, when you find the dot product, that's 4, we want the dot product to be 0. And we have 0, 0, 3, and if I dot that with that given vector, the first vector, so this is our new vector 2, and we have vector 1, which is 1, 1, 0. Those two vectors are orthogonal. Vector 2 is orthogonal to vector 1. And this can be 3, and we can scale that by whatever number we want to. It doesn't matter once we have it. This can be 10, 10, and then 0, and it's still going to be perpendicular to it, and we can change that now to a 1. So it's going to be 0, 0, 1. So 0, 0, 1 and 1, 1, 0. It's probably the easiest way to do that. The most simplified version of those two vectors. They are orthogonal. And later on, we can just say, all right, I'll just go ahead and give you a preview on this one. This is going to be 1 over square root 2, 1 over square root 2, right? And the square root of 2 is not random. It is the length of the vector 1, 1, 0. So now we found two vectors that are orthogonal, and they still have two pivots. Did I? Nope, this is vector 1, and that's vector 2. I just rewrote them. So what about if I have more vectors? And I want to find a basis for a subspace of R4, describe an orthogonal basis for W. Vector 3 is going to be in W. Now what are we talking about? Well, we're going to find out. So vector 1 is basically the same thing as x1. We're going to find vector 2 the same way we did it before. Vector 2 is going to be x2 minus y hat. How do we find y hat? That is something that's going to appear again and again. We took the dot product of those two vectors. We can call that x1. That never really changes. x1, 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 and then x1. So now we have vector 2, which is described as that one, right? So vector 3, we're going to do the same thing, but now we have to make sure that it's an orthogonal basis, which means that all of them are perpendicular. Vector 1, vector 2, they're already orthogonal by this method. Vector 3, we have to make sure it's perpendicular to vector 1. So we're going to start off with x3, and we are going to subtract x3 dotted with vector 1 over vector 1, vector 1, vector 1. And we also need to make sure that it's perpendicular to vector 2. And this is what we call the Gram-Schmidt process. And so what we're going to do is we're going to basically do the same thing. We want to make sure that vector 3 is also perpendicular to vector 2. So we got to take care of vector 2. And that new vector, this is going to be a vector minus a vector minus a vector, is going to be our third vector. We are using our given vector, and then we're just kind of manipulating that so that it is going to still be in W, still going to be in the subspace of R4, those three vectors. And we know that three vectors will still be a subspace of R4 because it's guaranteed to be there because the number of vectors is less than or equal, less than than the subspace that we're trying to span. So that is what we're going to do with this Gram-Schmidt process. So the Gram-Schmidt process is we're going to be given a basis, and that basis, those vectors, by the way, are independent. So it actually could even span R3 in this case, because we're starting off with independent vectors. That's kind of key, and all of them are going to be independent when we started off with them. So, and it really doesn't matter which one we use for x1. Sometimes I look at it and I'll just say, all right, the first one that I see, I'm going to call it x1. And so we're going to use that as our basis, as our starting point, as our foundation. And we're going to see how now we're going to kind of transform this one a little bit. So it's still going to span like the plane and whatnot. And as we're doing this, because this is very arithmetic and is very, so this is going to be our first step, and our second step is to find the second vector. The third step I want you to do, and this is really important, is I want you to check that you did it right, that you multiplied and add, and you're looking at the right vectors when you're doing that. You want to make sure that that vectors 1 and 2, the new vectors, are still orthogonal. That you didn't make any careless mistakes. And I should have had this video up like an hour ago, but I was looking through the notes and I found some errors because I didn't double check my work. So make sure you do that. So then we're going to find out what's up with the third vector. And then we want to check that the third vector that you created is still orthogonal to the first vector, and it's orthogonal to the second vector. And that's doing the dot product is relatively easy, and they're going to be relatively simple numbers. And I would say that you should stay away from fractions. It'll just make your math easier, but if you have a 4-function calculator, this will be fine. I think there's no row reduction really on this. Maybe we can keep going down to the number of times that we have. After each step, before you finalize it, you want to check that your vector was right. That it was still orthogonal. So if I have 3 vectors, what does that look like? And so the way we're going to do this, and I think I might have to go to a separate page on this, but we'll see. So are any of those vectors orthogonal? That answer is no, because they're all positive, so we don't have any negatives that cancel out with that. You can start, again, you can start wherever you want to. And I will show you kind of both of them, and I'm just going to do this on the next page, right? So we have these 3 vectors, and these 3 vectors are independent. We have 1, 2, 3, 0. And then we have, I'm going to make sure that I'll copy down my notes. We have that second vector, and we have, I am lying to you right now because 1, 2, 3, 0, 1, 2, 0, 0. So I was giving you the final answer. And 1, 2, 0, 0. Then the third, so this is x1, x2, and I'm going to do it this way. And x3 is 1, 0, 0, 1. Okay, so we want to find that, so these are not orthogonal. So we want to make them orthogonal. So I like to go ahead and I want to make these things orthogonal. I'm going to create them over here, and I'm going to just check. I just like to do mine right here. So this is vector 1. Vector 2 is going to be x2 minus x2, b1, 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 b1. So vector 2 is going to be 1, 2, 0, 0, my second vector, minus the dot product of these 2 vectors, which is 1 plus 4 is 5. And then the dot product of vector 1 and vector 1 is going to be 1 plus 4 plus 9, which is going to give you 14. And at this point, I'm going to go through this first one a little bit slowly. I'm going to take out my calculator and do 1 minus 5/14, which is 9/14. And then I have 2 minus 10/14, which is going to be 9/7 on the calculator. 0 minus 15/14 over 14. That's going to be negative 15 over 14. It's getting ugly, but it's okay. I promise you. And the third one is going to be 0 minus 0. Oh, good, right? So the second vector, I'm going to multiply this by 14, scale it by 14. It's going to give me 9, 18, negative 15, and 0. And I still don't want to do that math because I'm lazy. And I'm going to divide. Now I'm going to divide everything by 3. Because all we're doing is changing the magnitude of it. We're not changing the direction at all. So when I divide it by 3, what I get out is what I was writing before, which is 3, 6, -5, and 0. And then to check that that dot product is 0, 3 plus 12 is 15, minus 15 is 0. And so now we kind of have to do this one more time. I'm going to go ahead and keep that color. So x3 minus x3, vector 1 over vector 1, vector 1, vector 1, minus x3, vector 2 over vector 2, vector 2, vector 2. And those are dot products, and those are vectors, and we're going to get out vectors. So x3 is 1, 0, 0, 1, minus x3 v1, so I'm going to look at these two, 1, 0, 0, and it gives you 1. And then the magnitude of vector 1 is still going to be the same, 14. And vector 1 was 1, 2, 3, 0. Minus x3, which is up here. This is x3. And vector 2 is going to be 3 plus 0 plus 0. So it's going to give me just 3. And then the magnitude of that second vector is, unfortunately, 70. So this is where our calculator is going to come into play. And vector 2 was this 3, 6, -5, and 0. So when I do that, I just use my calculator. I get 1 minus 1/14 minus 9 over 70. And that gave me 0.8 or 4/5. And the next one gave me -2/5. The next one is 0. And the last one is 1. But I don't even want to deal with that math with fractions. So I'm going to multiply it by 5. And I'm going to get 4, -2, 0, and 5. And like I said before, now I'm going to do that fifth step, which is double check that we did it right. So that's vector 2, that's vector 3. So did I create one correct? So I have 4 minus 4 plus 0 plus 0 is 0. Those two vectors are orthogonal. And vector 2 and vector 3, 12 minus 12 plus 0 plus 0 is also 0. So we've created an orthogonal basis. Okay? Now, what made this math a little bit cumbersome, we'll say, is that I chose x1 to be that first vector, and I had to use that 14, and that 14 is just annoying, right? So it kind of doesn't matter what you choose, and I'm gonna, if all we're doing is finding an orthogonal basis that still spans the same thing, you could deal with the easier one first. So what I did is I called x1, I started off with that same one of 1, 0, 0, 1. That's what I called x1. And then I called x2 1, 2, 0, 0. So I'm really going in order. I'm placing them in order of magnitudes. And then the last one would have been 1, 2, 3, 0. And that just made the math a little bit easier. And when I did that, I called that one x1, I called that one x2, and I called that one x3. When I did that, we would obviously have the first vector is going to be 1, 0, 0, 1. I'm going to press pause, right? I'm going to write down all the work. You can press pause right now, and you'll see that there's the math right there. And you can look at that in a second instead of seeing me write that. So I had to press record on that first one, before I went to the third one, but that's how I did. That's vector 2, and now I'm going to press pause and do vector 3. And those two vectors are orthogonal. So when I use those other vectors, vector 1, so it was also helped out that we got 9/18 for x2, v2, 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 which gave me 1/2. And then we had a bunch of zeros in that one. So we had 0, 0, 3, 0. which is the same thing as 0, 0, 1, 0. So I had paused to check that those two the vectors 1 and 2 were orthogonal. Vector 3 times vector 1 is 0, bunch of zeros, and vector 3 times vector 2. There's only one non-zero number. And those three vectors are still, they form a basis, they are orthogonal, they are independent, which is the same thing as forming a basis for that one. Okay, so those are the first three examples, and everything else is really going to be the same thing. So let's look at the next one. So suppose the following is an orthogonal basis so we have that 1, 1, 0, and it's really the same thing as we had before, right? I think that's the same example, 1, 1, 0, and 0, 0, 3. So we can, just like we did before, we can change that 1/3. We could have changed it to 1, and we can rescale them to form unit vectors, and that'll be helpful later on. So that is still the same thing, going in the same direction, but now it's just a unit vector. So now we're going to use the Gram-Schmidt process to transform this basis. Kind of again, so we have these three vectors. So I think this is, I forgot where the error was on the notes, honestly, but we have these three vectors, and you want to choose wisely. Like, do you have any vectors that are orthogonal? And in this case, we do. And what I did is 0, 2, 1, 0. That's going to be the first vector. And I'm just writing them like this because it's easier for me to do dot products and things like that. And then analyze them a little bit. So I'm just going to write them out. 1, 2, 0, -1. And then we have 1, 0, 0, 1. So what I'm going to do is, is this first vector orthogonal to any of the other vectors? And if we started off with, and that answer is yes. So you could have started with this vector over here because it is orthogonal to that one. But the good news is that if I choose this one as x1, so there aren't three of them that are orthogonal, but there are some combinations. x1 is not orthogonal to x2, right, if I call it that one, but it is orthogonal to this vector. So I'm going to choose this one to be x1, the first one to be x1, and the last one to be x2. Because it's going to make our math a little bit easier. Hear me now and believe me later. Just choose, if you want to still choose that first one, that's fine. You can do lots of things as long as you check it and check that Gram-Schmidt process. And then I'll just go back and I'll choose that to be x3 and that to be x4. And then so we're going to create, I'm going to now write my orthogonal basis over here is 0, 2, 1, 0. The next one that I write must be orthogonal to it. And I'm just going to do this one, and then I'm going to erase it, right? So vector 2 is going to be x2 minus x2 v1 over v1, v1, v1. And so when we do the dot product of this one, x2 dotted with v1, and actually, since they're right beside each other, we can do it right here, 0 plus 0 plus 0 plus 0. So that is just going to give me 0. So the second vector that I'm going to write is just going to be this 1, 0, 0, 1 vector. So even though there are 4 vectors and it looks like it's going to be a lot, and it still kind of is, and it's a lot to kind of squeeze onto your page of notes, we'll go ahead and do the x3 one. So I like to write it out. Vector 3 is going to be x3 minus x3 v1. You could have done v2 right here. It really doesn't matter, as long as I just would suggest that you stay, whatever you choose to do on this one, you just keep it the same. I think that's going to be key. So now, it's because I've done this one and I've done it a bunch of times because I messed up. Now I'm just going to cheat and look at my notes on this one and start copying. And hopefully I copied everything down correctly. but I will pause on this one. So I have minus x3, actually I will look, x3 dot, well, they're right beside each other again. So that's going to be negative 2. And then the magnitude squared of that one, v1 dotted with v1 is going to be 5. And 0, 2, 1, 0. And you might already be kind of bored with this. And x3, that's going to, oh, the good news about this one is that x3 and vector 2, those two are orthogonal, right? So it's going to be minus 0. So, and then we are just going to have, whoops, I was looking at the wrong one, and I apologize for that. Looking at the wrong one. My eyes went to the wrong vectors. And then we have 1, 0, 0, 1. And that equals 1/2, negative 1/5, 2/5, and negative 1/2. I'm not going to go over like the arithmetic because it honestly is just arithmetic. And I would rather deal with whole numbers than fractions. So I have 5, negative 2, positive 4, negative 5. And I'm going to double check that those two vectors are orthogonal. So vector 1 and vector 3, they are orthogonal because I have negative 4 and positive 4, positive 5, and then we get a negative 5. So now I'm truly going to look at my notes on this one. This is when we get that 0. And I like to write it out, especially now. I can write it out pretty quickly. x3, v2, v2 dotted with v2, throwing a dot occasionally just to make it look good. And that should be x4. x4 dotted with v3, 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 v3. And now we're going to go ahead and copy what I had down for x4, which is 1, 2, 0, negative 1. Minus, just doing the math on that vector, magnitude of v1 is still going to be 5. The magnitude of that, whoops, and I didn't squeeze in my vector 1, which is 0, 2, 1, 0. Ugh. And then minus, though I got too excited about that one because I had a 0 in there. So it really doesn't matter what vector 2 is. I don't have to copy that one down. And then that's going to be 6 over 70. And then vector 3 is this 5, 2, negative 2, negative 5. And so definitely I cheated on this when I used my calculator. And I got 4/7, another 4/7, negative 8/7, and a negative 4/7. So what does that tell me? Well, really these two kind of have the same, these three have the same magnitude, and this is going to be twice the value of that one. So I can go back and I can say that vector 4 is just 1, 1. Somehow I changed colors. 1, 1, negative 2, negative 1. So that's the fourth vector. So we're going to double check that that's right. 0, 2, negative 2, 0. We're good. Vector 1 and vector 4 are perpendicular. 1, 0, 0, negative 1. We just need to check the ones that we're introducing now. 5 minus 2 is 3. Minus 8 is negative 3, plus 5 is 0. So that is now my new orthogonal basis, those 4 vectors. So those 4 vectors spanned R4, and now these new 4 vectors are perpendicular, and they still span all of R4. And that's the math that goes with that. It's all arithmetic. The Gram-Schmidt process is important. We're finding orthogonal vectors. So if A is an n by n matrix with linearly independent column vectors, which a lot of our matrices are, they're independent, and if Q is a matrix with orthonormal column vectors that results from applying the Gram-Schmidt process to the column vectors A, what relationship do A and Q have? Well, we have this other theorem. The short answer is A. The vector, the matrix that you're given is equal to, whoops, Q times R. And I know that I pressed this. A is equal to Q times R. That was supposed to be highlighted. So Q is the orthogonal basis for the column of A, and N by N is an upper triangular for column of A, and R is an N by N upper triangular invertible matrix with positive entries along the diagonal. And you'll see that. Finding Q is simple. All right, so Q transpose times Q is equal to I, since we had orthonormal columns. And Q transpose times Q is equal to I. That was in the other section. So A is equal to Q times R. So basically, you're going to form Q, and you know what A is, so you're going to figure out what R is. Q transpose times A. So Q transpose. So we really multiply both sides by Q transpose on the left. So Q transpose and Q transpose times Q is I. So Q transpose times A equals R. So we have to make those columns orthonormal. Orthonormal, again, just means that we're going to use those same things, but we have to be unit vectors. We're going to change the magnitude of it. We can't choose whatever we want to on this one. So we're going to find the QR factorization of this one. Well, we gotta find out what the heck Q is. That's really what the process is. So Q is going to be made up of the vectors. I'm going to do the vectors first. So the first vector is going to be, oh, we've already done this one before. So 1, 1, 0, this is the same thing as example number 1. And the second vector is going to be 0, 0, 1, or 0, 0, 3. It really doesn't matter. So the Q is going to be the orthonormal columns. So the magnitude of V is the square root of 2. 2. So it's going to be 1 over rad 2, 1 over rad 2, and 0. That's going to be the first vector, and we don't really have to normalize that one. It's going to be 0, 0, 1. We can just copy that in. If you had a 3 in there, then you would find the magnitude of that and divide by it, and you get 0, 0, 1. So that's kind of it. And now we're going to find out what Q transpose times A is, and that'll give me what R is. So Q transpose is going to be 1 radical 2, 1 radical 2, 0. And we can do this in our head, honestly. Most of the time, the math is going to be pretty simple. And then times A, we have 1, 1, 0. And then A was 2, 2, 3. So Q transpose times A. So this, because I'm slow, 2 by 3, and this a 3 by 2, we're going to have a 2 by 2, right? It's going back to just the basics. The first row by the first column, 1 over rad 2, 1 over rad 2 is 2 over rad 2, which is the same thing as radical 2. The first row by the second column is 2 over rad 2 plus 2 over rad 2. 4 over rad 2, when you can leave it as 4 over rad 2, that's fine, but we should know from our Algebra 2 days that that's just going to be the same thing as 2 over rad 2. Now, we said this thing was upper triangular, and we should remember what that is, but if you didn't, just do the process. The second row by the first column is 0 plus 0 plus 0, which is 0, which is good, upper triangular. And then we have 0 plus 0 plus 3, right? And so that is upper triangular since we only have values in the upper triangle. Okay? So that is what Q transpose A is. So we're saying that that is what R is. So the QR factorization, so we're saying that A is equal to Q times R. Q is 1 rad 2, 1 rad 2, 0, 0, 0, 1, times R. R is rad 2, 2 rad 2, 0, and 3. And if you were to multiply that out, you would get back R. You would get out a 3 by 2. And that is, I did not do that math. That's going to give you that 1, 1, 0, 2, 2, 3. And I'll let you do that math. and you can check that. I know that it's right, okay? So that's kind of it, honestly. The QR factorization. Now, when I'm building, I was thinking about this, like, wouldn't it have been easier if I had done something else? And I am still going to trust my process on this. Like, I'm going to keep the Q to be, so I'm going to build Q. Actually, I'm going to make the vectors first. I'm going to find those vectors first. I'm going to keep it the same, x1, x2, and x3. So I'm going to have 1, 1, 1 as the first vector. So the second vector, done this and I've double checked it. And I think this is the one that was wrong on the notes. Like I messed up somewhere. I didn't go back and find out where the error was. So minus, so vector 2 is obviously, and you kind of have your notes on this one, x2 minus x2 v1 over v1, v1, v1. So x2 dotted, so the dot product of those first two columns are 2, and the magnitude, the dot product of v1 and v1 is 3, and then we have 1, 1, 1, which gives us negative 2 thirds, positive 1/3, and positive 1/3. So this other vector is going to be negative 2, positive 1, positive 1. And I know I have not normalized that yet, so that's the third vector. Second vector, excuse me. The third vector is going to be 0, 0, 1 minus 1/3. This is x3 v1 stuff. And the first vector is 1, 1, 1 minus x3 dotted with v2, which is going to be 1/6. So because now we're looking at v2, the magnitude of that is 6. And then we have negative 2, positive 1, positive 1. So that gives me 0, negative 1/2, positive 1/2. So that third vector that is orthogonal is going to be 0, negative 1, positive 1. And again, I can't tell you how important it is to double check it. So I think I didn't double check that I made orthogonal vectors using those columns. So double checking that, we have 0, negative 1, positive 1. We're good. 0, negative 1, positive 1. We're good. So Q is going to be that first vector normalized, 1 over rad 3, 1 over rad 3, 1 over rad 3, and then negative 2 over rad 6, 1 over rad 6, 1 over rad 6, 0, negative 1 over rad 2, positive 1 over rad 2. That's what Q is. R, and then we got to figure out what R is. But in order to figure out what R is, you got to do Q transpose times A, which is going to be 1 over rad 3. It looks like I left out a radical 3 there. 1 over radical 3, 1 over radical 3, negative 2 over radical 6. So that second column is becoming the second row, and the third column is becoming the third row. And if I multiply that by A, and I literally did this by hand, and I got radical 3, 0, 0, 0, radical 6, 0, 0, 0, radical 2. Is it upper triangular? Yes, it is, right? It is at least upper triangular. Okay, so that is it. So there's the R value. That's the R matrix, and Q times A equals R. And then Q times R equals A. So if you multiply that, you would get back out A. And that's it. That is the very last thing we're going to have that's going to be quizzed on. I will go over like 6-5 probably together, like one of the last couple weeks of class. If you have any questions, please stop in during office hours.